Hi everyone and welcome to this, my video on applications of right angle triangles, part of my trigonometry series for general maths. Now if you don't know what that means, it doesn't actually matter. Right angle triangles are universal and you're probably watching this because you've had to. Well, thank you very much for watching. If you head over to mathsguru.com, there are lots of videos over there that might be useful, all right? Not just this one, lots of them. And if you can do me a massive favor and subscribe to my YouTube channel, that would be immense. Why? Because it just lets me know that you've watched. And if you can, leave a comment below, either on my website or on YouTube, and I'll be blown away, all right? Because nobody ever says nice things about math videos. Anyway, moving on. What are we going to do today? Know how to apply sokatoa. See, I can't help myself. Every time it's got to be said in the Japanese accent. To find the missing side lengths and angles in application style problems. Now, I know you hate application style problems. All of us do. But the good news about trigonometry is that if you can find a right angle triangle in the diagram anywhere, then you are sorted because you've already watched my previous videos. Yes, that's told you how to find side lengths and angles, and you are guns at this now. Well, as a quick recap, obviously right angle triangles have an arrow in the corner pointing to the hypotenuse, or in there the hypotenuse, yes, and then we have adjacents and opposite side lengths. We've discovered that actually just working out how to label the side and then formula, substitute and solve makes life so much easier. Now, Sokatawa helps us remember silly old Harry caught a herring trawling off America. Now, again, you've probably got no idea what that means unless you watched my first video about my maths teacher, Mr. White. But silly old Harry caught a herring trawling off America is the same as so, ka, toa. Right? So they're all just ways to help us remember. So here's my first example, believe it or not. And the point of it is here, if we look at the following example, while the words are there, and they may have provided a picture, we should be able to draw this because it says a flagpole. Now, I don't know about you, but if you've seen a flagpole, I'm pretty sure I know how to draw a flagpole. There is a flagpole, there is a flag. I don't care about the flag, it was just the pole. Let's say they put the flag away. The sun's rays make an angle of 38 degrees with the ground. Right, so the sun's rays, well, the sun does rays, he says. Let's bring that down. The sun does rays this way. At an angle of 38 degrees with the ground. Well, there's my ground. There is 38 degrees. And lo and behold, we have this, yeah? It casts a shadow of 7.42 meters long. That means the distance between there and there. And ultimately, I'm pretty sure it's going to say find the height of the flagpole. Now, how did I know it was going to say find the height? Because we have a right angle triangle. There is my right angle, okay? And I've got one side length and I've got an angle. The chances are they've got to ask me to find that other side length there, which just happens to be the height of the pole. So rubbing my diagram out, because theirs is way much better because it's got a sun in it, I'm going to now label that as X. And then just following the rules of trigonometry, I'm going to write Sokatoa. Well, first thing I'm going to do is label my side lengths. There is my angle. It's the I. It's looking at my opposite side length. There is my right angle that's pointing to my hypotenuse. And that has to be my adjacent. All right, okay, so color in the side lengths they've given me, or highlight. Well, that's one that I've got to find. And that is one they've given me. So in which case, I'm looking for something with O and A in it. So, ka, to. All right, O and A.